On, wait, which part of?
Oh,
this?
whatever.
The
I don't
front-
even honestly
Okay.
remember what was happening, so.
That's fine, we'll keep it that
That's
fine.
She's like, don't worry, don't worry. Just,
Yeah, so help me out, guide me, take me by the hand.
You can go first, Ken.
651.
Okay.
Let's start
6 what?
51. This is because we added more the day that you were not here.
Yeah. Son of a.
So do we want to talk about
Yeah,
yours
you
first?
would have had to watch
We
the
can talk about
recording
yours
to
first
know
then.
that.
Oh. Hey, Dr. T, chill out. Everybody chill out.
So do we want to talk about yours
Back
before
off.
this one?
Let's see, I gotta find the freaking problem.
Okay, it's.
I think
can
I'm
give
almost
you a
there.
page.
Oh, I'm there, I'm there.
Oh.
I'm close.
He's in the general.
I'm in the 6.5s. Okay. 6, shit.
All
Okay.
of the answers are at the, oh, not the answers, I mean the exercises are all at the back though.
Got it.
I was gonna say there are
And then the
answers in this
Conservative
book.
system, got it.
How could you have the answers would be longer than the book?
Yeah, they're
Yeah.
pretty basic answers in the back.
Yeah.
They're like, yes.
I didn't
Okay,
know
but
there were
how?
answers.
Just a few.
Okay, so we talked about finding a conservative quantity, and we talked about a conservative system.
Yes. So, yes,
Okay,
that's all, I all agree.
so
Yes.
no, I actually okay. My question is, I know what a conservative system is. I don't know what a conservative quantity is.
So for us, it's probably gonna be the energy, the potential energy.
Okay, so when it says find
Or the
a
total energy.
conservative quantity, we can just say
So here's what, we're assuming that our system, bless you, our systems are of this form. So that system there, is this is the negative derivative of the potential on this side. So when I have x dot equals, is it x minus x cubed, I think?
x cubed minus x.
X cubed minus x. Then this correlates. So dv dx,
That's x dot dot is equal to x cubed minus x.
that is, is x dot dot?
Yes.
Oh, okay, we gotta, okay. Then we need to convert this into a system,
Yes.
but, okay. Cool. So first thing I would introduce velocity, yeah. And then v dot is gonna be x double dot, and that's gonna be x cubed minus x.
Yes.
Yes.
Which then you can say x, y to make your life easier. That's what we
Yeah,
did in our
absolutely,
example.
100%. So that's gonna get you part C, and I don't know if
And
you've already
part
got
A.
that, and part A.
Which is great. I think I'm just confused on the instruction to
Find the conserved quantity. Yeah,
Because
so
to me, I would say the part that's the center, like there's a center and then there's two saddles.
yeah.
So then the conserved quantity is what lies in the center.
No, so okay, so let's talk about this.
Okay, good.
So a conserved quantity. So you've got solutions to this thing. You've got your x and v plane, and you've got, like you said, a center. I don't know where the center is, but probably it's 0, 0, right?
Correct.
And then you've got like saddles out here, like so, and then there's all sorts of interesting kind of weird things going on here. But the conserved quantity is a quantity that on these trajectories, on a solution to this equation, it remains constant. And that's going to be the energy. And so take a look at, I don't know if that makes sense, but so think about like total energy, Kayla, and how there's like a change between potential and kinetic, right?
Yeah.
But the sum is always constant in a conservative system. So the potential energy plus the kinetic
Yeah.
is constant.
Okay.
So that total energy is the conserved quantity.
Okay.
once you're on a solution to the system. So, I'm looking for the page that gives us exactly what we need.
Because I found a couple of like theorems, like it can't have any attractive points, it can't have.
Yes, so, I actually had this is actually what I meant to say here with X double dot. So if you look on page 159. They lay out how to find this potential. So they're saying that in a conservative system, a second order conservative system, this is the relationship between the acceleration and the potential. So we have this, so then this thing here, when you rewrite it, it looks like this. And in more specificity, if you look onto the next page, they kind of keep this going. But the key here is to simply take the antiderivative of this. Because the negative antiderivative. Because this thing here, this is negative dv dx right here. And the potential's the conserved quantity. So what I'm going to do here is set dv dx equal to negative the thing that's on the right side of the equation. And then just solve that for x,
Okay.
which is pretty easy. I mean, it's just like integrating.
So it should be a function. A conserved
Oh,
function should
absolutely.
be a function.
Yes, it will be a function of x,
Okay.
x alone.
Okay. I don't know why, but when I read that,
That's
I was
okay.
like, quantity means scalar.
And it is a scalar. This is a scalar quantity.
Because it's always the same.
Yes. And it has a single valued output.
Okay.
Yeah.
It should be.
Does that help? Does that make sense?
Yes. I think maybe I had turned my brain off too many hours and I was like,
It's all good.
SOS.
Easy question, that answer. Happy to help. Does this sound good on this, like how to proceed?
Yes, thank you.
Okay,
That was,
yeah.
I mean, the rest of this problem is like all of the other problems that we do. It's
Yes.
just like,
It's just this
Hello?
then. Yeah, but you can use Y's if you want, that's all good, not a problem. If that feels better. More questions?
for me, okay.
Sure, or whoever.
Do you want me to do that?
Yeah, go ahead.
This probably answers the next question I have based off of what we just talked about.
Okay.
So for 652,
Yes.
A and B are exactly the same
Yep.
process. And then C says find an equation for the homoclinic orbit.
Now that becomes interesting.
So that's not the same process.
No. So let's
Right.
take a look at that,
Let's
okay?
take a look.
Okay.
Please and thank you.
You got it.
Do you need an eraser?
Probably.
Okay.
Yeah, I'm starting to
Is there-
realize that, like, just now.
Is this a new
We're gonna,
box?
we're gonna do some of
There you
this. Thank you. Oh, thank you for confidence. So helpful.
So you're gonna leave here with like a black palm.
What's new? As long as I don't rub it all over my face, everything's actually improved. Okay, so 652, let's see here. So we've got a simpler system. Okay, so we've got x double dot equals x minus x squared. Okay, cool. And let's get the phase portrait out. So convert to a system first. So if you want, I'll use y. I'm happy to do that.
We don't have to, that's just how we did our example for the potential energy system, so I just did what we did.
Cool. I almost kind of have to just do this because that makes
Yeah,
sense to me.
sure.
So that's how I remember how to start, just
Then
the velocity. Yeah.
Can change my brain. Okay.
It's okay. No, and I'm happy. And look how easy it is.
Wow.
Oh shit. We can just
Holy
pretend
moly.
it's a y even
Perfect.
in our
I
mind.
got you.
Okay, cool. So, and then v dot is going to equal x minus x squared. Because that's x double dot. So then we get our Jacobian, and
that's gonna be 0, 1, 1 minus 2x, 0. Looking good? Yep. And fixed points, so fixed points, clearly v needs to be 0. So that's a must, and then this gives me two alternatives, either x equals 0 or x equals 1.
Yep.
Yeah,
Agreed.
cool. So let's get our faceplate out. So we got 0, 0, and 0, 1. Now we're gonna classify.
I think I disagree with you,
Oh, well, good.
because it's a x versus v, so when that second coordinate be on the x,
Thank you. Yeah, you're right. Yeah, I wrote them ass backwards here, so you are absolutely right, friend. Thank you. Good call.
it just would have been upside down, which
No,
is
no,
okay.
yeah, but you're keeping me straight.
So it's 1, 0.
All right.
Yes.
So yes, 1, 0. So then we have j of zip is going to be 0. That looks like that's a saddle right there, right? So because we have the delta is -1, tau is 0, that is, if anyone was ever wondering how you classify these points with the Jacobian.
I did find that.
Good.
I did find that
Good.
in my notes. I was
Good.
like, oh, wait, I could use this.
Yes,
This
you
is
can. Good. And so, yeah, so you can go to this little diagram. It makes life real easy, right? You just need these two quantities. Sometimes it's tricky in here. This quantity's a little tricky sometimes, but you can always just look at this, and that'll tell you which of these two sides you're on, if that's positive or negative. So this is a saddle, so there's nothing to mess with on that. So we've got a saddle here at, where was that, zip? Okay, so saddle. And then at 1, 0, what do we got? Looks like a center, probably.
Agreed.
Yeah. So we have, now we have delta is +1, tau is 0, so that's on here. Right? So definitely a predicted center.
Just for clarification,
Yes.
which quantity told you that that's a center?
That delta is +1. This is my delta axis, this is my tau axis.
Which
Okay.
means that your lambda will be in the complex. Which
Yeah,
means
so
that-
remember, we had this, the characteristic polynomial is this. And then when you put that in here, you're gonna get tau squared, and then delta +1 equals 0. And then the roots of this are plus or minus I.
Okay, so a positive delta is a center or just
Well, you gotta be
complex?
careful with tau equals 0. So if delta is positive, you're on this half of the plane, and then when tau is 0, you're on this line.
Uh-huh,
When tau is positive, you're in this region, and this is either an unstable spiral
right.
or an unstable node or one of these degenerate things on the line. And then this is stable down here. Everybody's stable.
Oh, okay.
Spirals and then nodes.
Okay,
Yeah.
yeah, that makes sense.
So this is a center. So, all right, what the hell was the problem?
We're
Yeah.
finding the
Homoclinic orbit. Yes. So, let's see, if we do this saddle, let's actually do a little bit of detail on that saddle. So this was my Jacobian. We've got, let's see, let's find the, I think it's gonna be lambda equals plus or minus 1. So at 0, 0, these are my eigenvalues. I'm absolutely positive of that. So let's get the eigenvectors. I think they're gonna be the diagonals, but let's just check, and we'll do 1. So let's say lambda equals 1, and then I'm gonna take that and subtract 1 from the diagonals. And then I'm gonna look for the vector in the null space of that. So that says, can you see here that V1 and V2 have to be equal for this to be true? So that dotted with that, right? Negative V1 plus V2 is 0. So v1 equals v2, and then for lambda equals -1, it's gonna be v1 equals -v2. Just seen that enough times in my life to know that's what's gonna happen. So we've got this. Now we need to figure out where the flow is here. So I'm just gonna like take a small point up in here. So let's say we've got x equals epsilon, y equals epsilon, and epsilon is small and positive. So then I go to the original system. This should be v, sorry, v equals epsilon. And we get x dot equals epsilon, so positive flow in the x direction, and then v dot equals epsilon minus epsilon squared. So this is positive. Why is this positive? Why is this also positive? Because epsilon's super tiny, because epsilon's like, if epsilon was a 10th, this would be a 10th minus 100th. So when epsilon's small, this gets smaller, so they're both positive, so that means I have like a flow up to the right. Got x dot is positive, y dot is positive. So that tells me this is one of the sourcing manifolds for the, so that's your source manifold, your output manifold. And then here's your input. This must be your input manifold because it's a saddle. And then this whole thing starts to come into clarity here because we see the center here. We even now know the rotational direction. It's got to be consistent with the saddles, right? So you got to have a clockwise flow. And the homoclinic orbit is one of these centers that, see, all the centers in here look like this, and then we get to that outer edge, and we got that. So now I'm kind of in the wilderness with you. So let's see if we can figure out what to do here, because I don't know what to do.
Okay.
Yeah.
Cool.
Yeah. I have no freaking clue what to do for that homoclinic orbit. So this is exciting, actually. Really good shit.
So does that mean that, let me make a question.
Yeah, please.
So, shouldn't there be like a range where homoclinic orbits occur?
What do you mean?
Okay, let me clarify. I thought a homoclinic orbit was where it comes to a point.
It does.
So
Yes.
then, at some point, it's those centers. So then for a range of time, it's either a center or it's a homoclinic orbit?
Well, I don't know if I'd say range of time. I think it depends on maybe the state. So at any particular instant, x and v have values, right? And if those values land you inside here, then you'll have cyclic behavior.
Okay, yes.
If x and v are just perfect to land on that fragile manifold, that fragile trajectory there, then they'll be in the homoclinic orbit and leave from here and then come back to there.
Got
So
it.
does that
So
help?
there's only one homoclinic orbit?
There's actually two, but it's just like the same, it's kind of the same thing, just on the other side. There's
Okay.
only one on this side.
Okay. How do we have the homoclinic orbit on the other side if we don't have?
Oh shit, we don't. You're right. Sorry, Kayla. I was like inserting a center over here that doesn't exist. So
That's okay.
yes, ma'am, you are
So
absolutely
we only
correct.
have one.
Correct.
Great.
Absolutely.
This is making way more sense.
So then, and then this stuff over here is all kind of like, right? This is classic saddle action over there.
Yes. Okay.
Yeah.
Perfect.
So let me take a look, because I don't quite, I'm gonna see if he just gives any tips on how to start with this so we don't flail too long on it. Okay. Here's some. I want to see where the first homoclinic orbit is. Okay, there it is. Because I've never done this. That's one of the exciting things about this class. I don't know that he does that. Can anybody just check through, it's kind of like should be in the reversible. Let's see, from page 161 onward, I'm just looking for computation. Because it looks like it's gonna be weird, that's for sure. Oh, so the energy, the conserved quantity will be constant on any trajectory, so it'll be constant on the heteroclinic orbit or homoclinic orbit. So if we take our potential, but why would it not depend on V?
I did just see that, wait, maybe I didn't see anything.
I'm just thinking the energy equation should give us, oh, yeah, okay. I think I got it. I think I know what we need to do.
Okay.
So, let me get a fresh pen for this. That's kind of exciting. All right, so, you would agree that if this is a conservative system, then the energy will be conserved on that homoclinic orbit.
Agreed.
We agree with that, yeah? So what we need to do is find the conserved quantity, which we probably did in another problem, and then just find any point on this orbit and use that point to figure out the constant of integration. There's like a constant in that potential, or there should be. So let's take a look. So in other words, we'll find the energy level on this quantity, right here. Sorry, let me be a little more clear. We're going to come up with some energy equals some function of x and v. We're going to figure out a point on that orbit. We're going to plug it in here. So let's say x naught v naught is on the orbit. Then we're going to figure out what E naught is at that point. So find the energy level on that orbit. And it'll be unique because each of those has a unique energy level. And then the equation we're looking for is just going to be f of xv equals E naught. And then that should describe that orbit. So we just need to get that orbit. So all right, let's just figure out, let me just go back just a little bit here. Here we go. So yeah, if you look on page 161, kind of about halfway down, that E that he's got there, that's what I'm thinking of for this.
1/2 y squared.
Yes, 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 yes. So let's see, how does he get that? Well, so his equation would be, since we're using V's instead of Y's, let's see, I just want to convert his into, so this is his energy equation. And that 1/2, I know where this comes from. This part right here is just the potential that we're given. So this is V of x. That's easy to find for us. That's the antiderivative of that. So for us, the negative integral of x minus x squared is going to be negative 1/2 x minus 1/3 plus 1/3 x cubed. And then we got to figure out what this is. And I knew at one point, I've known several times, and I forget it every single time, how he got that. Because he's just integrating, let's see here. Let's see. That's y, that's x naught. How does he get that? see, if you took the derivative of this with respect to time, you would get v. Oh. Yeah, okay, so. That's 1/2 v. Derivative of that is this. So somehow, how do we get v dot? Oh, look, okay, got it, okay, I'm with it. Okay, so take this equation here and multiply through by x dot. So we're gonna take this equation and I'm going to multiply by x dot on each side. So I'm gonna get v x dot equals x minus x squared x dot. And then this left side, this is actually the derivative, since v depends on x, this is the derivative with respect to time of 1/2 v squared. Check it out, chain, is that right? Wait. Oh, no, yeah, one more step. This is it. So x dot is also the same as v. So x dot equals v, so this is actually v dot equals x minus x squared x dot. And now I see a couple chain rules going on here. So on the left, this is the derivative with respect to time of 1/2 v, assuming v is a function of t. Does that make sense? Check that out, because I know I'm kind of like sputtering here, but I'm sputtering toward victory. V squared, ooh, sorry, there we go. That'll make it.
Perfect, I got you.
There you go, you're with me
Yes.
now, okay? Sydney, you cool
I'm
on this?
not with you.
So how would you take the derivative of this? You would use the chain rule. So you do the derivative, because I'm differentiating with respect to a variable other than the variable that's here.
Oh.
But I know that v is a function of t, so do the outside first. So what's the derivative of v squared with respect to v? 2v, bring that out in front, times the half, you get the v. So that's the derivative of the outside, times the derivative of the inside, so that's just v dot.
Okay,
Yeah?
I'm better now.
Okay, good.
I'm better now.
And then this side is ddt of, actually 1/2 x squared minus 1/3 x cubed.
So why now are we not taking the negative?
I already, oh, didn't I? I didn't. No, thanks. Kayla, wait.
Because
Wait a minute.
we said that v dot, wait.
Oh, because I'm doing a different, I'm actually doing a
This is
slightly
totally
different.
different?
This is kind of different.
Great.
So I'm not going back to what was the potential and trying to identify that. Yeah, no, that's
Okay.
good. I'm like actually just manipulating directly these equations.
Perfect.
So, good question. So now that I'm down here, let's move everything to one side. So this is actually ddt of 1/2 v squared minus 1/2 x squared plus 1/3 x cubed equals 0. And what this is saying is that this quantity does not change with respect to time.
Right.
So it's conserved. So this is my conserved quantity right here. So I'm going to integrate both sides with respect to t. So then you integrate, and we've got 1/2 v squared minus 1/2 x squared plus 1/3 x cubed equals a constant. And that constant is the energy. So this is actually the energy level for that curve. Now we just need to get a point that's on there and fix that up, set that up. I feel like it should be 0
I like 0.
because 0 is on that trajectory, right? Like 0 is the one point we know for sure. It's like where it starts and ends.
So then E equals 0.
Yeah, equals 0. So the energy's totally 0 on there. There's a balance
between the kinetic and the potential energy on that thing. And I mean, and this thing is, there's subtraction going on here, right? So we're saying that like, so let's put 0 here because 0, 0 is on the trajectory. So we're saying the kinetic and potential energies are always equal, I think, along here. Because this is like your kinetic energy.
Does this seem right? Because it's got velocity in there.
This
Well,
seems
I
right,
thought
yeah.
that so V now is not potential energy, because previously we said.
No, it's unfortunate. There's a capital V floating around that represents the potential. So this is just velocity.
Great.
So it makes sense that this is kinetic and this is the potential energy.
Yes. Agreed.
So I'm kind of curious if we plot that out on Desmos. Can we get some laptops on here, please? I got my little thing's doing that, so I can't shit. Actually, it's kind of like perfect time for me to go do my P-rig.
Absolutely.
Let me go do that. And could you, give me a Desmos plot of that, please. You'll need to use implicit form.
You simply do not have to do
Oh, it's cute.
What am I Desmos seeing at? Bottom equation?
Yeah.
You're just so
Wow.
What?
That's kind of cute.
Did we get a two-sided like figure 8? Oh wow. But
It's-
that works, doesn't it?
What did you, wait, let me make sure that we got the
That
same.
looks freaking good.
Okay.
Yeah. That is called, I think it's like the Witch of Ignacy or something like.
The what?
The Witch of
Okay.
Ignacy. There's a curve that, can you look that up for me really quick, please? Witch of, and it's AG, and, I mean, this was made back when like, monks were just even bigger assholes than they are today, but.
This, ooh,
Oh, it's not that then, okay.
that is very.
But that is really cool, I've never
cool,
seen
though.
the circle thing with it. I didn't know it like rode a
Wow.
circle for a while.
That's kind of cool.
There's this looks like some Da Vinci stuff, like he's got like all this.
It
Yeah.
does, yeah, it totally does, that's super Da Vinci out. But that
Is Da
whole
Vinci a
curve.
monk? No, I'm just kidding, sorry.
Yeah, I don't know if he was that big an asshole. So those other ends here, those are actually in our graph as well. It actually, because this is the conserved quantity, right? So if this thing is constant in this picture, that represents a trajectory. So what we're seeing on the other side are just the manifolds for this saddle on that side.
So that's why we don't see our other half of our
Yeah,
Okay.
yeah, cause it actually represents the system, cause when I was walking back, I was thinking, oh, we're gonna see this, but that doesn't make sense. Because if we did see this, then that would also be, you know, represented, that, if we did see this, this would be the equation. Because we'd have to have that, whatever, I don't wanna, that's the picture, I'm just babbling now. That's enough babbling. Enough of that shit. That was fun. Holy hell. Give me some more stuff to fun with. Sydney, you got some.
I do.
Let's give you a few moments here.
Okay, on. Okay, I need help getting a phase portrait of
For,
631. Because if I can get one for 631, then I can do 632 and 636.
okay, cool. So let's walk through the steps.
Yeah.
You're
So I did the fixed points and the Jacobian, and I think I got the stability for them.
Okay, let's
Yeah,
take a
yeah.
look. So 631. No good,
No good.
no good, pen.
Silly pen.
Okay, 631, we've got x dot equals x minus y dot equals x squared minus 4. That's the one, right?
Yeah.
So what did you get for your fixed points?
So x has to equal, if x equals 2 or negative 2,
Solid.
and then x has to equal y, so then 2 or negative 2.
I like all that, that's great. What'd you get for your Jacobian?
1, negative 1, 2x0.
Even better, or just as good. So then we plug in our points, so j at 2, 2 is 1, negative 1, 4 zip. And then at negative 2, it's got a negative 4 down there. Does this all sound right?
Yeah.
Cool, so our determinant here is gonna be positive 4. Trace is 1, excuse
Yeah.
me. So that immediately puts me in this realm
Up top. Yeah.
up top. And so then my question is, am I in here, here, or here? And that'll tell me completely what I need to know. Because I don't know at this point how I sit relative to this parabola, right? So these are spirals. So this whole thing, this is unstable, right, up in this region. This is stable. This is spirals inside here. So either unstable or stable spirals. And then the centers are that transition area right here. And then here is where things start to turn into less of a spiral. So along this line, what you see are things that look like that. You get this it's like I want to be a spiral, I just don't have the energy to, or something like that. Maybe there's too, I don't know what energy is.
Oh, that makes sense. Because I was looking at when I used that,
But these are stable.
like the graphing thing where you can make all the trajectories on it, that's what I was seeing, and I was like, that doesn't look like
Well, we'll
it.
check it out, and
Yeah.
we'll find out, because I'm actually thinking, oh no, okay, yeah.
Okay.
So what, this equation of this parabola is 4 delta equals tau squared. Now let's check out what, in here, is this 4 delta greater than tau squared or 4 delta less than tau squared? And the way to check is to just take a point on this axis where tau is 0 and delta is positive inside here. So notice that tau is 0 here and 4 delta is always going to be bigger than it. So in this inside part here, we've got 4 delta greater than tau squared. This is 4 delta equals tau squared. So this is 4 delta less than tau squared. In that little pocket, that little cuspy pocket up in the top. So what do we have here?
Oh, there we go. I was missing
What do we got for each of our?
So for you have 2 as your first one. 4 delta would be 16, and that's greater than tau squared, so that's on the, yeah, that one.
So we're in here, so what do we got?
Unstable spiral.
So we've got an unstable spiral at 2, 2. And then what about at -2, -2? Tell me what we got there.
That's a saddle.
Yeah, perfect, awesome, because you, as soon as this is the case, you're done, right?
Yeah.
So you've got an unstable spiral here, or excuse me, a saddle, like you just said, here, and then this is an unstable spiral. So at this point, if you were doing this by hand, Sydney, I would just like take a point nearby here and figure out which way you're spinning. I mean, really what you just need to know is, am I spiraling out like that, or am I spiraling out like that? Does that make sense?
I think so.
So, yeah, so you're either going clockwise or counterclockwise. So I would just look at the flow here, and so let me show you what I mean. Let's be more precise. Let's say x equals 2.1 and y equals 2.1. So we're going to take a point just a little to the top right of it. And let's look at the vector there. So we go back to the original system. Notice that x dot equals 0. Oh, that's handy. And y dot is going to be bigger than, so this is a little
Positive.
bigger than 4, it's positive, yeah. So I've got no horizontal change, only vertical change here, and it's up. So that shows me I'm spiraling counterclockwise. Does that make sense, how that all worked?
Yeah.
Groovy. And then down here on the saddle, you just have to figure out where your nodes are. I kind of got a feeling there's something, I guess there can't be a manifold down here like this, because this, well, probably not, but possibly. Let's see, so have you done any work with the saddle, like what's going on down here?
All I did was look at the graph of it.
Okay, well, let's actually get a little more in detail on that one then. So let's look at -2, -2, and here's our Jacobian. So we're gonna get the eigenvalues for this, so that's gonna be lambda squared minus 1 lambda plus -4 equals 0. So I'm using this equation here, that lambda squared minus tau lambda plus delta equals 0. And so this is lambda squared minus lambda minus 4 equals 0. I don't think there's any nice factorization of that that I can think of. And so lambda equals 1 plus or minus root b squared 1 minus 4. So that would become a plus 16 in there. This is nice, okay. And that's fucking horrible.
It doesn't look fun, no.
It doesn't look fun. It doesn't look fun at all, but let's just keep with the not funness of all of this. I'm gonna subtract that off. This is like welcome back from break day. Hello.
Happy Monday, friends.
Happy Monday. So first, let's find the eigenvector corresponding to 1 plus root 17 over 2.
Yeah.
So yeah, I'm going to subtract it off of the diagonal here. So we're going to get 1 minus a half, which will become positive a half, and then minus root 17 halves. That's not too bad. I mean, it's not great.
It's not the coolest thing I've ever seen, but
No, I've seen cooler things too, I agree. And so then when we subtract it off here, it's actually gonna be 1 minus, no, 0, so negative a half, minus root 17 halves. Because you don't have that plus 1 on it. So you notice these two differ by just plus 1.
yeah.
Okay, so the legend goes that this should be consistent.
So I've been told.
So we've been told. Let's go with this top one because it's got a 1 in it. That's pretty sweet. So this top one actually says that 1/2 minus root 17 halves V1 equals V2. Tell me if you agree with that.
1/2 minus
from, I'm just looking at this, dotted with this, yeah?
Yeah.
So we get this. So now I'm gonna set V1 equal to 1, and that means V2 is this 1/2 minus root 17 halves. Now you might think that looks fucking horrible,
Well, yeah.
but it's approximately, let's just, we just wanna understand approximately, we're not doing brain surgery here, hopefully.
Hope not.
Yeah. I hope we have better tools for that. So this is like square root of 16 halves, that's like 4 halves, that's like minus 2, so this is approximately minus 3 halves. Does that make sense? See how I'm getting that? So, over in the picture, so for the saddle manifolds, we're gonna have this one that is like 1 to the right minus 3 halves, so it's a little steeper than diagonal. And then there's one on the other side. And that corresponds to a positive eigenvalue, so that's our source. And then really that's all I care about, and then we'll just say, something else like that for the other one, no doubt. And that one's gonna be a sink. And do we even have a picture going yet? No. Oh, here, kind of. I kind of got a
Oh, there it
picture. So let's see, so I had said that, this doesn't seem consistent, does it? Because I was kind of expecting an input here and an output there just because of the spiral bullshit going on. Hey, can we get a Desmos plot of this thing, please? I want to see what's going on, because it's possible they are. Oh, wow, okay. So let's see, are we even thinking right on this?
Yes.
Yeah, we are. It totally looks right. Oh. Okay, so this is what I want to see what happened. Oh, okay.
You're almost done.
Yeah, really almost done. Yeah, you're right, Kayla. Okay, this is okay. So I think that this picture could use a little more precision,
Yeah.
But what happens is we see that, so we're getting stuff like, I don't know, does it look like there's a little cycle forming? Because it kind of, yeah.
That's not.
That looks good. No, I
But
think
it's.
it looks cool.
Yeah, I
what
mean,
you've
it
done there.
matches what you're doing.
Yeah, what I'm wondering is this thing contained? And I guess the answer is no. Hold on, do you mind if I change something
No,
here,
go
my
for it.
friend? I just want to see a bigger picture, more than anything. So I want X to go out to like 8, and then Y to go out to 8, and just get a better sense. Here's what I'm doing, just to see, what's going on out here. Okay, so there is no containment. Ooh, that's beautiful. That's cool. It's really gorgeous. So what we do see is, it's like a swooping hair. It's like Starry Night.
Yeah.
This is some serious Starry Night shit, right? That is just like going off like that.
So that's what Van Gogh was on about.
That was what Van Gogh was all
He was just
doing.
like,
He was actually a genius.
Yeah.
He just didn't know it.
Okay, that was fun.
just doing some super complex math stuff,
Yo. Yeah.
throwing it down.
I used the phrase sus in calculus, and everybody looked at me like,
My dad's been on.
just knock it off.
My dad's been on about sus. It's like one of his favorite terms.
It's
to use now.
great.
Yeah.
It's so tight and like easy to say and perfect.
I mean, at least sometimes my dad doesn't know, like, it's not the right context.
Yes.
I'm like,
Oh,
okay, Nick. Like, I appreciate the effort,
Nick.
but no. Yeah. Nick is my father.
Do you ever say that, like, oh, that burrito slapped?
Yeah.
Ooh, I've never said that.
My personal favorite is that was gas.
That was gas.
Gas. Yeah.
My mom and I were eating
That's an
lunch
old-
the other day.
oldie. Oh,
gas,
no.
yeah.
Yeah.
She goes, oh, that was on slap. And I was like,
You said, well,
I was like,
Did you
that
say
was,
no cap? Or
Or
No cap.
No, they don't. But she looked at me and she was like, right? And I was like, yeah.
See, her logic was there.
She
She
was
knew.
there.
She knew what she wanted to say, and she said it almost.
She was like so
It was
close.
so close.
It was perfect.
It's
I was
cute.
like, that was on
It's
slap.
very cute. Yeah.
That was
on
You know
slap.
what? You're right. I've been wrong this entire time. It's on slap.
I think I'm gonna start using that.
On
Just because
slap.
it'll throw everybody off. Yeah.
That was on slap. Damn.
Everyone's gonna be like, what?
And then I like smiled really hard and she's like, what? And I was like, nothing.
You did
Your
great.
mom,
perfect.
your mom
You
is
did
amazing.
great.
She is. I love my mom.
My brother, one of my oldest brother, he hasn't figured out how to use the word whack yet. Like, oh, that's so whack. Like, okay, whack is not good, right? It's not like, it's like stupid or dumb. It's,
Yeah.
But he was like, he'll be playing his game or whatever, and he was like, yeah, it was a really good game. It was so whack, and I was like, you just contradicted
You're
yourself.
disagreeing with yourself. What's going
No,
on?
and I'm like, no, trust me, I'm the one who knows what I'm talking about here. This is like my generation term. Like don't ever say that again. Like,
It's like sometimes sick can mean it's awesome and sometimes it's like not
Yeah.
awesome.
Yeah.
That
yeah.
one totally context based.
I
yeah,
feel like it's more like that's awesome these days.
Yeah.
Right? That's totally sick. Like,
Mhm.
yeah.
Unless you use
You're
it
Trinity
super
and you are sick.
sarcastically.
I mean,
Unless what?
unless you're Trinity and you are sick.
Oh yeah.
Then-
That's not cool.
Definitely not
Face.
awesome.
Not awesome.
Not awesome.
That's not sick.
0 out of 5 stars. Would not recommend. I'm not really sure how we
Next
got
problem.
here.
Next
Yeah,
problem. It's
sorry,
all good.
sorry.
It flowed naturally from whatever was happening. What else do you want to talk about?
Okay, rabbits and sheep.
Yay.
I can do fixed points. I can now do the phase portrait. Null clines.
Oh, okay. That's cool. Let's review this because we're going to need it on Wednesday. So this is great. You're just helping out.
I'm glad that my lack of knowledge of null clines could be useful.
I mean, isn't that all of school is a lack of knowledge? You're like, impart knowledge in me.
Yeah. Well, at the last scholarship activity, there was like only three students there, and two of them were like, I don't know why they were even there. They didn't seem to enjoy math at all. Well, one of the girls who was there was just like getting very upset, very frustrated because she wasn't quite understanding everything. And I was like, are you okay?
Welcome to
And she's like, right, yeah. And she said, I just don't like it when I don't immediately understand stuff. And like the students who were there
yeah.
helping me were like, college, that's next 4 years, so that's gonna be painful.
Dude, I cruised through high school. So my freshman year of college, I was like, I don't understand this. Like, why am I dumb? Like, I was pissed off because I didn't understand anything. And I was like, damn, I guess it just happens in college. And I got used to it. And I
I
was
mean, hopefully you're learning something, right?
I am.
You know? So like,
I just,
it's a lot of money to pay to just like
You
hang
think?
out.
I'm paying for,
Told that you're right.
I'm paying for no hot water. That's what I'm paying for.
That's bullshit. You should get something, like a free pizza every day that goes on.
Write a
They don't
strongly
care.
worded letter.
They
They really
don't.
don't.
You know?
They really don't.
Is that what, and you get that vibe from them?
Yeah.
I had a room that smelled like cat piss for months and they didn't care. And then they went, we're actually replacing it tomorrow, you need to be out. This happened right before fall break. They're like, you need to be out of your room by
Wow.
tomorrow.
One
I was
thing,
like, great, I leave for break today. So,
they literally
they don't
like,
care.
no. And if you put in a work order, you can put in a work order
It doesn't matter.
4 times for the same thing.
Yep.
It's not. I have people like on the second floor who are like, "Oh no, dude, I put that in on the first day of school, and it's been broken for
Wow.
the entire time." We have
We have
people
missing
whose heaters
furniture.
don't work, furniture.
You have missing furniture, broken furniture.
Well, luckily it's a good
Broken
deal
lights.
financially, right?
Yeah.
Yeah.
What a
You know
steal
what?
it is living
Yeah.
here.
Jeez. Anyways, yeah. Sorry, no clients.
No
My bad.
clients.
Sorry.
When I worked at IBM.
You worked at IBM?
Oh yeah.
Yeah.
I didn't know that.
Yeah, for 7 years before I came here. Got like 14 patents.
As you should. As you should.
Patent from IBM. Yeah, on image processing stuff. But yeah, I had this whole other life that I hated before I came here.
He was
But now
miserable.
you're here.
Now I'm here. Oh yeah.
And now we talk crap about physical plant and lack of hot water and whack and sus
So true.
every
So,
day.
What were you
No
gonna
cap.
say about it?
Okay.
What were you gonna say about at
Oh,
IBM?
so, cause it reminded me the cat urine smell. One day, I would come in really early and I like to be there by myself in the morning so I could count it as work and do nothing.
Yes.
So I would get in really early, and I was in this phase for a long time where I just wore white t-shirts. And they were pretty nasty for the most part. You know, I was not really, it wasn't until I met Amy and she started helping me buy clothes that I started wearing nice clothes.
Yeah, women will do that for you.
Yeah, she's like, why is everything like 5 sizes too big? You know this doesn't look great. So, yeah, because I was just like ripped cords and white
Oh,
t-shirts and a
Jesus, Dr.
flannel.
T.
That was like, I
Oh,
was
God.
grunge, like total
Really?
grunge. So I was in my office and I was like, ah, man, it smells terrible in here. And I just kept, whatever I was doing, it wasn't working. And then I realized, I was like, God, that is terrible. And I realized one of our cats had urinated all over the shirt I was wearing.
Oh.
You ever smelled cat piss?
Yeah.
It ain't good.
No.
So bad.
So there was this giant yellow stain in the back of it, and I was just like, well, I guess this is what I'm doing today.
Personally, I would have taken my hobby ass home.
Oh
I-
yeah, I would have
yeah.
gone home and changed.
I should have.
Or I would have found a lab coat and been like, this is my outfit
I would
today.
have bleached myself, maybe. I'm not.
I
I
think
mean,
I probably just closed the door and took my shirt off. And I was like shirtless
like
or
shoved it
something.
in the corner.
he
Yeah.
put a
Bye.
"not in the office today" sign. He said, "Listen, guys."
It didn't make them dislike me anymore because that couldn't happen. So,
Fair.
Why didn't they like
well, I don't know. I didn't like them either.
Oh, it's mutual. It's fine.
It's-
It's acceptable.
If
It
it's
was
mutual,
bad
it's
job.
yeah, it's not.
It sucked. I just didn't like it at all. But it was this like chance I got, and I was like, okay, try it, you know.
Tried it.
But like a 9 to 5, only 2 weeks of vacation. That
No.
not for a guy like me.
But now we're here,
Now we're here.
and this doesn't make you miserable.
No, there's some parts of it that make me unhappy,
That's fair.
but it's a pretty blessed.
It's like I'm not gonna lie to you. There are
Like just, you know,
pieces.
working with my students, that's like the best part. And
Grading
then
papers,
everything else. Yeah, there's ways. I've gotten pretty good at not doing that. managed my load, managed my workload. A lot of web work.
Yeah.
A lot of web work.
I remember the web work days.
Yeah.
Oh, instant feedback.
Yeah, like there. Do you know
It's-
Dr. Springer? Was she here when she was in the math department and she quit? Yeah, she was here and she got tenure and then quit. Dude, she was like so fucking unhappy constantly. She didn't know. She was always like, "Oh, I'm just working all the time. I'm just working all." She also thought she was like the smartest person in the room
Oh.
constantly. And we're like, "If you're so smart, why are you working so fucking hard?"
Dr. T's like, personally, I
Right?
could never.
Yeah, no. I mean,
Work smarter, not harder.
work smarter,
Absolutely.
not harder. So she was just always anyway.
She needed web work in her life. That's what she needed.
Well, now she's just like a yoga Krav Maga teacher.
Is she happier?
I guess.
I hope so.
I mean, if you do yoga all day, you better be freaking
Yeah, you
happy.
better be
Like
happy.
You
that's
better be enlightened as fuck.
you're just like doing great.
You would think. She wanted to have a baby too, so I know
Oh,
she had a
love.
kid, and
Yeah,
she
maybe
was
she needs to do yoga.
she
Kids
was
are-
pretty miserable. But she was also that was really irritating. That, like you spent 6 years like with this colleague, and like we hired her and hoped she'd stay, and then she quit. She just quit. She like went on a sabbatical and just was like, I won't be back. It didn't
Oh.
tell us till the end of the sabbatical.
Oh, cute. Oh.
Yeah.
Did she?
very
Do you
nice.
get paid at sabbatical?
Yeah, she got paid half. She did a full year, and you get like half pay for the year. So like a semester, you get paid. You can
Okay.
do a full. You can get full pay for 1 semester. If you do 2 semesters, you get half pay for the whole year.
Oh, that's fair.
But she really said like, thanks for the money, I'm out.
Oh, she didn't even say thanks.
There was no thanks involved.
Yeah.
You know what? I hope her yoga is miserable.
Oh.
Oh no,
How
no.
rude.
We hope. Yeah, she was. Yeah, I was. No, Dr. Hawk
I love Suzanne.
is an asshole.
What?
She was. I don't know. Anyway, sorry.
No, Clyde!
She really fucked us over bad. So let's do these isoclines and I'll bitch more then.
No clients.
No clients, thank you. So, okay, which one did I assign?
641 through 643.
Oh shit, well, okay. So let's do 642.
Okay, love that. Where's my 642? Hello, where are you? There you go.
Alright, so we want those face portraits. So the null clients are the places, there's more than two, where either x dot is 0 or y dot is 0. Those are the null clients.
Not simultaneously, so not like.
Sometimes, I mean, they will, where they intersect, then we'll have both these simultaneously 0.
Okay.
So for the null clients, the first thing we're gonna do is, we're gonna set x dot equal to 0 and figure out where that means, because on that then, Sydney, on such a trajectory, we know that x is purely vertical, or excuse me, the vector is purely vertical, because
Okay.
there's no horizontal component. Does
Yeah.
that make sense?
Yeah.
And then we gotta figure out if it's up or down, but, so set x dot equal to 0, and so that means we're gonna have x times 3 minus 2x minus y equals 0. So either x equals 0 or 3 minus 2x minus y equals 0. And this is the y-axis. And for these Lacoupe-Volterra models, you can just worry about the positive quadrant,
Yeah.
the purely positive. And then here, this is 3 equals 2x plus y. So when x equals 0, y equals 3. And when y equals 0, x equals 3 halves. So I'm getting the equation of that line. And I probably should just make it solid because I'm about to put little dashes on it anyway. So this, try color, you can, like doing this with color would sure make it easier to just keep straight in your head. But here's one of the null clients, and here's another. And along all of these, I have pure vertical chains. So on this thing here, and you just have to like figure out what it is, what the direction is, but I'm pretty sure it's like gonna be something like that. Do you see how to do that?
Yeah.
Okay.
And then when you put your y dot equal to 0, those ones are purely horizontal.
Yeah.
Okay.
Yeah, exactly. So this other one goes like this, and I don't know if that's up or down. Looks like it should, well, I don't know. I don't know. We'll have to like figure it out because this is confusing here. So,
This one is,
what's that?
I said this one's really cool.
Is it cool? No, you don't have to be sorry. You never have to be sorry.
Don't be sorry, Kayla.
Please, never. And then this one, let's do the other null clients. So y dot equals 0 when y equals 0, or x plus y equals 2. So x plus y equals 2 is like this, kind of. There's 2. And along there I've got pure horizontal change. Like that. And so that, and then the other place is the x-axis, right? So all along there, we've got just horizontal change. And this probably keeps going.
Okay.
Just looking.
Yeah.
Yeah. And so that's what they mean by the null clients. And then you still need to get like a couple direction arrows here. I got a feeling, I don't know, Kayla, you sound like you did this one.
Yes.
Is that kind of, does this seem right, like that?
I think so. I think I just, hold on, I think I went straight to drawing the face portrait because,
That's okay.
so I don't think I necessarily did the null clients. And even though it says right there, draw the null clients. But it was like
Silly
this.
Oh, wow. Yeah, that looks quite nice. Yeah, that syncs.
So in here, where might you suggest drawing? Because
So,
it's kind of busy.
so like you've got, yeah, it is very busy.
It's-
So
it
I
is.
would maybe just take another pen,
Okay.
color,
and draw
but
the
you can
null
see
clients.
that the way you've got those null clients, these guys are gonna be the tops of those,
Yes.
right? So yeah, they're gonna just hit there, and like that's gonna be the peak, and then, yeah,
They're so pretty.
they are pretty. Or whatever, I don't quite know how that goes. Does that help on that, Sydney?
Yeah, I just need a refresher on null coins.
Okay, so we're almost at the end of our time. Is there anything else question-wise? Maybe I could get these by Friday if you need more time. Or if you got it now, I'll take it now.
Not quite.
Okay,
Close
cool.
though.
What's close?
Pretty
Nice,
close.
nice.
Can I ask a super fast
Please.
question? Okay, would you come look at my computer screen for favor?
Yeah.
Because I don't know how to.
Oh my God, that's awesome.
Okay, so this is 663.
Yes.
So where I didn't. Yeah, that one. It
Beautiful.
looks really cool. It looks like this.
What the
Okay. So
I'm sorry.
I'm trying to classify points.
Yes,
Don't
ma'am.
tell me it
So,
tells you to draw
I
a
know
face
that
portrait.
when x is an odd multiple and y
It's a
is an
sketch
even
face
multiple,
Yeah.
we're gonna get a center.
Yeah.
And then
Dude,
the
that
flip
looks
is
cool
true
as fuck.
too. So like
Looks
these,
sick, but it says we have to sketch it.
No longer looks cool as fuck.
so like
No.
these guys,
Can I
so
put in the
this,
screenshot?
this
Yes.
is the
I have
first case, and
something
then
else
this,
sketch it
this,
for me.
this, so the second case.
Uh-huh.
So I'm trying to figure out how to identify the
Saddles.
saddles, because it, sometimes it's when x is equal to y, but there's also like a whole bunch of cases where it's just like,
So let's see, what are the other cases here? Yeah,
so
so,
these are just the center cases.
well, what if they're both even and they're both odd? Cause I think that's where the centers happen. So you've got two cases out of the four possibilities.
Pi, pi,
Oh, and you're throwing in pies?
okay,
Cool.
So that looks like an,
No.
and then
Odd.
we went 6,
that looks like odd odd.
6, okay, so it is, so even, odd, odd, okay.
Yes, and I think that when you have even or odd, you're gonna have saddles, but then the manifolds will change, like where the input
Yes.
and output part
Okay.
is. Yeah.
Thank you.
You're welcome. Well, that was a fun day back.
That's not. This is.
Thanks, friends. We will be taking